Hi. Last time, in the end of the last lecture, I drew a sketch showing the phenomena of wetting and non-wetting. So we had a vessel with water and a capillary tube immersed into this vessel, a capillary tube made of glass. And in this case, we know that water is wetting the glass, and so the surface of water will be somewhat deflected. And also, if the diameter of this capillary is small, say let it be less than 1 millimeter, it may be considerably less than 1 millimeter. It may be 1/10 of a millimeter. So in this case, the surface of water will look like this. If we repeat the same experiment with mercury and immerse a glass tube of the same small diameter in mercury, then the situation will be different. The surface will be deflected in the opposite direction, and the mercury will have this type of surface here. Originally, during the last lecture, I put it in a different way. I draw this surface something like this, but this was a mistake, certainly. This was a mistake, and the actual surface of mercury will be like this. So, this is the case when the liquid is wetting the surface of the capillary tube made of glass. And this is another case when the liquid is non-wetting. It's non-wetting the surface of capillary tube, of glass capillary tube. And so we have, in the case of non-wetting, we have a convex surface. And in case of wetting, we have a concave surface if we look from above, downward, from the atmosphere into the liquid. So this is a concave surface and a convex surface. And the surface of water in such a small capillary tube is called a meniscus. The meniscus here is convex, and the meniscus here is concave. So we know what is the difference of pressures if we have a surface of liquid which is not flat but having a shape of some sphere, having a spherical shape. If this radius is known, that is, the radius will be half the diameter of the capillary tube, then the pressure difference is known. That is, if here we have a pressure of atmosphere and here inside we have a pressure of liquid, then pressure of atmosphere minus the pressure of liquid at this point will be equal to 2 sigma over the radius of curvature of this surface. So sigma, I remind you, is a surface tension. Also, it's called the surface energy of liquid. If we go down, then we know that the pressure of liquid here Something's wrong. Что-то не так. Может быть. Идет, да? Okay, we continue. So we consider the pressure difference at the curved surface of liquid. If the surface is not flat, if it has some curvature, some radius of curvature, then the pressure difference on both sides of such liquid surface will be given by this formula which we have derived, which we have already derived, where sigma is the surface tension, or also it's called, this quantity is also called the surface energy. So if we go downward in this liquid to its surface, then let it be h, the height of this water column inside the capillary tube, let us denote it by h. Then we know that at point 2, the pressure P2 will be higher because of the pressure of this water column. And so at point 2, the pressure will be higher than at point 1, exactly by the formula, the density of liquid, the acceleration of free fall, and the height of this water column. So we know that the pressure at this point, if this point is on the level of water surface, then the pressure at this level will be equal to atmospheric pressure. So the pressure at point 2 is atmospheric pressure. And so combining these two equations, we may obtain that 2 from here, 2 sigma over r should equal to this quantity, which is rho gh. And from here we obtain that sigma, the surface tension, equals 1/2 of rho gh times radius of this capillary tube. So if we know the radius of capillary tube, and we certainly know the density of liquid, and certainly we know the acceleration of free fall, the only thing remaining to measure, which remains to measure, is the height of this water column. If we measure this height, then we can calculate the surface tension of liquid. And the same will be true here for this case when the liquid is non-wetting, but in this case we will have to measure this height h. So in any way it's possible to measure. This is the method of measuring the surface tension of liquid, and that was the information I wanted to give you during the last lecture, but we had practically no time, not enough time. And today I wanted to start a new topic which is electrostatics. So in this course of Introduction to Physics, we consider some most important topics included in the secondary school physics program, and we have no time to consider all the topics which are studied at the secondary school, because in half a year it's impossible to cover all the topics. But we have chosen the most important topics, and now that will be electrostatics. To begin with, I would like to remind you that all matter around us consists of atoms and molecules, and an atom, if we consider an atom, it consists of a small nucleus and an electric cloud around the nucleus. The nucleus is positively charged while electrons are negatively charged. The nucleus of an atom is very small. Its diameter is approximately 10,000 smaller than the diameter of the atom itself. The diameter of nucleus is about 10,000 smaller than the diameter of atom. And the total charge, electric charge of all the electrons in the electric clouds equals the total electric charge of the nucleus. So how can we, as the atom, therefore the atom is neutral because the electric charges cancel each other. How can we take the electron out of this atom? And how can we separate an electron? How can we separate an electron and take it away? There are several possible methods. First, in chemical reactions, electrons sometimes leave their own atom and stick to other atoms. That is the process accompanied, which is the core of chemical reactions, accompanying the different chemical reactions. Another way to take the electron out of atom is to heat the atom, is to heat this substance. In heating, some of the electrons will go away and the atoms will remain, which will have unbalanced positive charge. Also, it's possible to take the electron out of atom by illuminating the substance using for example, gamma rays, gamma radiation. A gamma radiation a gamma quantum will be absorbed sometimes, and the electron will take all the energy of the gamma quantum, and so the electron will have enough kinetic energy to fly away from the original atom. In this case, the atom will bear some positive charge, unbalanced positive charge, and the negatively charged electron will go away. Such an atom which is positively charged, which is missing one or two electrons or more, such an atom is called ion. The ion, and hence the process of separating electrons from atoms is called ionization. Ionization. And the gamma radiation, which may cause such a separation of electron from ions from atoms, is called ionizing radiation. Ionizing radiation, it means that the radiation capable of ionizing atoms, that is, capable of taking electrons away from atoms. And there is another possibility to take the electron out of an atom, that is by friction. If we have some other substance here, other substance which has its own atoms and own electron clouds, it may so happen that electrons may stick to other atoms and go to another piece, another body. So that sometimes happens when we arrange friction between two surfaces. In friction, the electrons sometimes jump to another body, jump to a different surface. And for this reason, the one surface, the first body and the second body, which are in friction, so this we move in different directions. So in some cases, the electrons jump from one surface to another surface. And in this way, one surface will be charged positively and another surface of another body will be charged negatively. If the two substances are identical, then this process takes place both in one direction and in the opposite direction equally. And due to symmetry, due to identical properties of these substances, the number of electrons that jump to another surface will be the same. The same number will jump in opposite direction, and therefore no macroscopic electric charge will be observed on these surfaces. So if we arrange friction between identical surfaces, well, practically the charge there will be no charge, or the charge will be very small. But if the substances are different, if we take different material, like amber and wool, then electrons will jump intensively from one body to another body, and we will have an electric charge finally due to friction. This is the most simple, the most primitive way to obtain electrically charged bodies. And this method was known for thousands of years. And people long ago noticed, centuries and centuries ago, noticed that if we take a piece of wool and an amber and in friction of amber and wool, the piece of amber then after friction will attract some small bodies, like small leaves, or hair or something like that. And today you may notice that when you comb your hair with a comb, if you comb dry hair, not wet but dry hair, then your hair will be attracted to the comb. That is also the electric interaction due to the fact that in friction the surfaces of these bodies participating in friction are charged, electrically charged. And the process of charging is electrification. If you want to charge, you electrify the body. To electrify the body, I repeat, there are several different methods. You may electrify a body by friction, or you may electrify a body by illuminating it using ionizing radiation, or you may electrify a body also by dissolving these atoms in a solution in water, for example. When a substance is dissolved in water, electrons sometimes are taken away and stick to the molecules of water, and the remaining atomic core, lacking one electron, will have a non-balanced positive charge, and this will be an ion floating in liquid, and another ion will be a negatively charged molecule of water with the electrons sticking to it, with the electrons stuck to this molecule. So in a solution, in water solution of different substances, we will observe ions, positively charged ions and negatively charged ions. So there are many possible ways to take electron out of atom, and in this way to electrify some portion of matter, some body. So in this way, if we electrify a small ball which hangs on a silk thread, and another small ball, similar small ball, which is on a silk thread, if we electrify these two balls in a similar way, and they will obtain similar charges, we say like charges, then we will observe that these two balls hanging on the threads will be repulsed from each other, and this repulsion will be very noticeable. It will be easily observed because the balls will be deflected, the thread will be deflected, and the balls will be repulsed from each other by some force of repulsion, and it will look something like that. So when we experiment with the charged bodies, we notice that some substances do not allow the electricity to flow away, and some other substances easily conduct electricity. If we take here some wire instead of silk thread, and this wire is somehow connected to the earth, then, and in this case the same, then no electrifying is possible, no charge will be kept on these two balls, and there will be no force of interaction. So some substances may transmit electric charges easily. Other substances, like silk thread, other substances do not transmit electric charges. And in this way, different substances are called conductors and insulators. Conductors are those substances which easily conduct electric charges, electricity, and insulators are substances which do not conduct, which do not allow electric charges to flow easily. So silk thread is an example of an insulator. There are a lot of insulators around us. Any plastic material is actually an insulator. Any dielectric is an insulator. A dielectric like amber. Amber is very good insulator. So porcelain is very good insulator. So by measuring forces acting between the balls and by changing the distance between balls, it's possible to investigate how this force of interaction, electrical interaction, depends on the distance between the balls, how this force depends on the distance r between the two charged bodies. The experiments were made, such experiments were made by Coulomb. Coulomb, a French physicist, Charles Coulomb, he investigated this issue, and he found that the force of interaction between two charged particles is inversely proportional to the square of the distance between the two particles. Also, he investigated how this force depends on the magnitude of electric charge. And before we go to the electric charge magnitude, electric charge value, we have to discuss how can we change the electric charge which is on a single ball. Well, it's very simple procedure. We can take one electrified ball and touch it with another similar ball, which is kept on some insulating rod. We keep this rod, we may keep it, that may act as a handle. We keep this rod, and a similar metal ball will touch the electrified ball. In this case, the charge which was originally on this electrified ball will be divided equally between the two balls, and so we may divide the charge by touching. So original charge, say Q, will be divided, and we will have charges Q over 2. And then the ball with the charge Q over 2 may be again touched with some other similar ball, and another act of division of charge will take place, and we will obtain charge Q over 4. And then you remember that originally there were two balls which had this charge, and if another ball now has this charge, we may touch the two balls, and the resulting charge will be the same. That will be 3Q over 4. The two balls after touching. So that was the first ball, that is the second ball, and that is the third ball. And if we touch ball number 2 and ball number 3, we will obtain this charge 3 over 4 of the initial charge Q. So by touching charged balls and non-charged balls, we can divide charges in different proportions, and we can change the amount of charge kept on a ball, and so we can study how the force of interaction depends on the amount of electrical charge contained in an electrified ball. And Charles Coulomb made this experiment, and he discovered that the force is proportional to the amount of electric charge on one ball and is proportional on the amount of electric charge on another ball. So this ball carries charge Q1, and this ball has charge Q2, and so the interaction force between the two small balls is directly proportional to the quantity of charge contained on each of the balls, and inversely proportional to the square of the distance between the two balls. So F may be written as some coefficient of proportionality which depends on the units of measurement, and then the product of charges, electric charges, and the distance between the point charges squared. This is the Coulomb law, which was discovered practically 100 years after Isaac Newton discovered his law of universal gravitation, which looks similarly. Only in Newton's law of universal gravitation we have masses of two gravitating bodies, two gravitating point masses. And in electrical interaction we have charges, electrical charges here instead of masses. But the law, the Coulomb's law was discovered about 100 years later. If I'm not mistaken, it was the year like 1786, something like that, if I'm not mistaken. Something like that. That is 100 years later, 100 years after Newton discovered his law of universal gravitation, which looks similarly. So, when the charges are, when we electrify the two balls using the same procedure, the charges will be the same. And in this case, the two balls will experience repulsion. We say the like charges are repulsed from one another. But it's also possible to arrange for attraction of two balls. How can we charge a ball with an opposite charge? This process can be easily realized can be easily implemented by the procedure which is called electrification through induction. What is the electrification through induction? Suppose we have a ball which is charged using some procedure and bears some charge, and the ball is hanging on a silk. It's hanging on a silk thread, and we take another ball, similar ball, which is not charged and which is kept on a rod made of insulator, and we may use this rod as a handle, and so we may take this ball and put it near the initial ball which is charged. Just not touch it, but put it near the ball. And then we may connect the second ball by a wire with the earth. What will happen in this case? Electrons here will repulse the like charges, the electrons from here, and the electrons here will go down to the earth. And so this ball will obtain some positive charge. Well, these two charges will not necessarily be equal. The positive charge may be somewhat less than the initial negative charge, but because electrons here in the second ball are repulsed from the first ball, they will go to the ground, and some positive charge will be here on this ball. And if then we disconnect this wire, disconnect it from the ball, then this ball will bear opposite charge. So it's possible to arrange for opposite charges, for unlike charges to be on two balls. And it's well known, you should know that the like charges are engaged in repulsion, while the unlike charges are attracted to one another. The like charges repulsed, while unlike charges are attracted to one another. So between minus and plus we will have attraction, the force of attraction. And between two like charges like plus and plus we will have repulsion. That is very well described by this formula. If two charges are of the same sign, then the force will have like positive, two charges positive, and the force will be positive. If you change the sign of one charge from positive to negative, then the minus sign will be here. The force will be minus original force. It means that the direction of this vector will be different. And then if you change the sign of another charge, that will again be minus, then minus by minus will give you a plus, and the force will again change direction. So repulsion will be changed by attraction, and attraction will be changed into repulsion if you change the sign of any charge here. So we have repeated the elementary things which you should know, and all this is very well described in your textbook by Landsberg, the first chapter in the second volume. So I advise you to read the first 2 chapters, which are devoted to electrostatics, in the second volume of the Landsberg textbook. There are a lot of interesting things. All the experiments are described in detail, and many more experiments are discussed there, which illustrate the electrostatics and laws of electrostatics. I strongly urge you to read the 2 first chapters of the second volume of Landsberg. And now a few words about the units of measurement. Units of measurement of charges. In the international system, so MC, the charge is measured in coulombs. The 1 coulomb is to commemorate the scientist who discovered the Coulomb law of interaction of point charges. So 1 coulomb is the unit of measurement of charge in SI system. And distance is measured in meters and force is measured in units. So we know the units of measurement of this constant K. The constant K is necessarily measured in watt. It should give newtons as a result of this formula, newtons, and in order to compensate the 2 coulombs, the coulombs must be in denominator, and also meters must be somehow compensated, so meters squared should be here. Such will be the unit of measurement of this constant K. And in the international system, if we use coulombs to measure these charges, then this constant K will have the quantity 9 times 10 to the 9th degree, with the units of measurement indicated there. This value was obtained experimentally, actually. If you know how to obtain the charge of 1 coulomb, actually this is very large charge, a very large amount of charge which is never dealt with. You will never deal with such a huge charge as 1 coulomb. Actually, you will deal always with, and people have charges in laboratories like millions and billions of parts of coulomb. Because if you take 2 charges, 2-point charges of 1 coulomb, this is 1 coulomb, suppose this is 1 coulomb, and this is also 1 coulomb, and suppose the distance between them is 1 meter, then the force will be 9 billion newtons. That is about 1 billion kilograms. That will be million tons. 1,000,000 tons. If you take 2-point charges separated by the distance of 1 meter, and each charge is of 1 coulomb, then the force of interaction will be 1,000,000 tons, which is such a huge force which can never be reproduced in any laboratory. No material will bear such as stress, such a great force. So actually what charges people have in any experiments with charges are millions of times smaller than a coulomb. why people have chosen such a large amount of charge? A coulomb is defined as it's such a charge. 1 coulomb is such a charge which is transmitted through a wire during 1 second if there is if the force is 1 ampere, if the force of current is 1 ampere. So it's 1 ampere 1 second by 1 second. So that 1 ampere is a charge of 1 coulomb transmitted during 1 second. A coulomb per second. A coulomb per second, that is the current of 1 ampere. So coulomb is defined by the strength of current. It's more convenient to define the charge using the current strength. It's more convenient than to define the charge using the Coulomb's force. Technically, for technical reasons, for the reasons of precision in measurements, it's more convenient to define the unit of charge, 1 coulomb, using the strength of a current. So what is 1 ampere? We will discuss it later when we discuss constant currents. And now I have to tell you another curious thing. In many formulas of electricity and magnetism, some coefficients emerge, some coefficients like 4 pi and something else. And in many important formulas, people don't like to have this 4 pi coefficient, which is a consequence of Maxwell's equations, as a matter of fact. So people wanted to eliminate this unwanted coefficient from important formulas which electrical engineers often use. The formulas often used by electrical engineers, they should not contain such complicated coefficients, people believed. And so they wanted to exclude such coefficients from those important formulas. And for this reason, this coefficient appeared here. And for this reason, the force of the Coulomb's force is written in such a way that the K constant proportionality is chosen to be 1 over 4 pi epsilon 0. So that the force of interaction of 2-point charges will be 2 pi epsilon 0 Q1, Q2 over distance squared. And this epsilon 0 is called electrical constant, and it can easily be derived from here, from this definition. Epsilon 0 will be 1 over 4 pi K. That will be 1 over 4 pi, and we know what is K. That is 9 by 10 to the 9th power. And you can carry out these calculations, and the result will be and I hate remembering such quantities. So the result will be in the international system. This is electrical constant, which is in an international system of units, which enters the formula for the Coulomb's force of interaction of point charges, 2-point charges. So I repeat that all these issues are explained in greater detail in the first 2 chapters of the textbook of physics, of elementary physics by Landsberg, which you are recommended to read. And not only to read, but to make notes and to remember what is most important in these chapters. So now the next thing we have to discuss is an electric field. So if 2 point charges interact, like charge plus Q and the charge, another charge Q. If these 2 point charges interact, there is some force acting on the first charge, and there is some force acting on the second charge. Certainly, due to Newton's third law, these two forces are equal in magnitude and oppositely directed. That goes without saying. But there is another question. If we are in vacuum, absolute emptiness, then how does this charge know that it must be acted upon by some force from another charge? If there is absolute emptiness here, how is this interaction transmitted from one charge to another charge? When people thought about this issue, they understood that absolute emptiness does not exist. Even if we are in vacuum, vacuum is not absolute nothing. There is something in the space. And this something is called physical vacuum. And physical vacuum is very complicated, it's a very complex object, because physical vacuum is capable of transmitting all sorts of interactions, like gravitational interaction, electromagnetic interaction. All radio waves can go through, travel through vacuum, and optical waves can travel through vacuum. So vacuum, physical vacuum, is the medium which transmits interaction. Such is the modern understanding of all interactions. All interactions are transmitted through a physical vacuum, which is not an absolute emptiness. Physical vacuum, from the modern point of view, is filled with quantum fields. But from classical point of view, there is a field which which is around any charged particle. Any charged body creates a field around itself, an electric field. And this field should be perceived as some distortion of physical vacuum. We say some excitation of physical vacuum. This word is also possible. Some distortion of vacuum or some excitation of vacuum. So that is the field. That is some peculiar state of physical vacuum which is not absolute emptiness, which is something which we don't know what exactly is there. Nobody knows what exactly, but something should be there. Something should be there. Because if you have nothing here, absolute emptiness, then no interaction will be transmitted. No waves could travel. No waves, nothing could travel, nothing could be transmitted through nothing. Well, so people came to a concept of field. An electric field is something which is created by an electric charge. How can we describe the field? The field created by the charge capital Q must depend on this Q and must certainly depend on the distance from this charge. But the field created by this charge should not depend on any other charge which we bring here to this field, to this point in space. So if we take the force of interaction, in this particular case, the force of interaction will be the coefficient K, capital Q, small q, r squared. If we divide this formula by small q, then we obtain that force of interaction divided by q equals coefficient of proportionality capital Q and r squared. So this quantity does not depend on the outside charge brought here in this point. This quantity depends only on the central charge which creates the field in this space. So this quantity was believed to characterize the strength of electric field, and it's usually indicated as E. So if we know the strength of electric field in any point, here for example, if we know the strength of electric field, then it's possible to calculate the force acting on any charge put in this point. The force of interaction will be Q times E. That will be the force. And as the force is a vector quantity, then the field strength E is also a vector quantity. In any point around the charged body, anywhere, there is a field. And the field in any point has its field strength. Here we have field strength, and here, for example, E1, and here we have another field strength, E2, all of them being vectors. And here we have another field strength, E3, all of them vectors, and so on. In any point of space, you will have a field which is characterized by its vector of field strength. So the field created by a charge is characterized by vectors of field strength. What is a vector of field strength? Looking at this formula, we may understand the physical meaning of this vector. This is the force acting on a unit charge. If charge Q is 1 Coulomb, then we will have that, we will arrive at this relationship that the field strength is just the force acting on a unit charge placed at this particular point where we consider the field strength. So if we have a positive charge, a positively charged particle, then any positive probe charge, we call this small q charge a probe charge because we use it to probe the field in any point. So any positive probe charge will be acted upon by such force, and it means that the field intensity, the field strength, will be directed along the line connecting the two charges and will be directed from the central positive charge. And also in this direction there will be vectors of field strength, and in this direction, and so on. If we put a probe charge in any point in space, we will have a force acting on this probe charge, and hence we will have a field strength in this particular point. So in order to illustrate the field, we illustrate the field by drawing such lines, which are called field lines or force lines, electric field lines, and this is such a line along which the field strength is directed at any point of this line. We may choose a different point, and there will also be a field line going through this point, because at any point in space there is a force acting on a probe charge which is placed in this point, and at any point in space, hence there will be a field strength, some vector of field strength. If we take a negatively charged particle, then a positive probe charge will be attracted to the negative, and so the same field lines, electric field lines, going along radii, but the direction of field strength will be different. It will be opposite to the case of positive central charge. So the negative point charge will have such a picture of field created by it, created by this charge in the space around it. What if we have two charges instead of one? What if we have a positive charge and a negative charge? Then any probe particle put in this point, an arbitrary point of space, will experience a force of interaction with a positive charge. Force of interaction. If it's a positive probe charge, it will be repulsed from the central charge plus Q. And also it will be attracted to the negative charge minus Q. And therefore, these two forces of repulsion from one charge and attraction to another charge will be added according to a vector rule of addition of forces. And so the resulting electric field strength here at this point will be described by a vector sum of two field strengths. That is the first field strength originating from the first charge, and that is the second field strength originating from the action of the second negative charge. And therefore, as forces are added according to a vector rule, the net force, the net field strength will be directed here. This should be considered as an experimental result. Experiments show that the forces acting on a probe charge add according to vector addition rule, addition of vectors. So if we move to another point, the same picture will be there, and if we move to another point, the same picture. So if we are on the line connecting the two charges, 2-point charges, the field strength will be directed here from positive to negative charge. And if we are on a different line, the field strength line will be this one and this one, and so on. It's possible to draw as many lines as you wish. All the field lines describing the picture of electrostatic field. So the field line has a direction which shows the direction of force acting on a probe particle placed in this point of space. And so wherever you put the probe particle, you can find easily the direction of force, which will be a tangent line to the field strength line of electric field strength in the space. So the lines of electric field strengths are filling all the space around, and the picture is like this. This is called the principle of superposition of electric fields, or principle of composition of electric fields. So we have one electric field created by positive charge and another electric field created by negative charge, by another charge, and so the two fields compose a resulting field, which will be a vector sum of two fields. So this is a principle of composition of two fields, also called the principle of superposition of two fields. Superposition or composition is just created by a vector sum of two fields, two or more fields, a vector sum. This is the picture of classical electrostatic fields. Such picture is valid for classical electrostatic fields. In quantum physics, the picture is somewhat different, because in quantum physics, the principle of composition does not always work correctly. Sometimes it fails. There are situations in quantum physics when the superposition principle does not work. And this is due to the fact that in quantum physics, the electric field is believed to be composed of virtual particles, in this case virtual photons. And virtual photons are created at random and absorbed at random. And so in quantum field theory, the electrostatic field is fluctuating. And as it's fluctuating, both fields, this one and this one, are fluctuating. It's not always possible to understand what will be the direction of composition of these two fields, because at one moment this field may be zero, close to zero, and there will be only this field, and in another moment this field may be close to zero, and this one will fluctuate to have a larger quantity. So the resultant vector will have no definite direction, and only some average direction averaged over a long period of time can be calculated as this one, as according to classical rules. So the resulting field in quantum field theory is the average vector averaged over some period of time. But if you take a very short period of time, then the principle of superposition will not work. The classical principle of composition of fields. So if we talk about the electric field lines, we have to underline some properties of electric field lines. An electric field line can always be drawn through any point in space, whatever point you choose. And if you put your probe charge here, point charge, small charge here, then there will be some force acting on it, force resulting from superposition of fields. And so there will be some force, and some force will be tangent to a field line passing through this point. So electric field line can always be drawn through any point in space. Another property of electric field lines, they do never intersect. The two lines will never intersect. It's impossible that this line goes and intersects another line. This is absolutely impossible, because if you put a probe charge here, there will be a definite force acting on it in definite direction, and not two different directions for a force, but just one direction. So the two electric field lines can never intersect. And another property of field lines is that they do not terminate at any point other than an electric charge. So the field line, if it goes here, it will terminate on another charge. It may not terminate somewhere in space, like here. It may not terminate in space. It will go until it meets another charge. Never terminates in space. That's impossible. And another property is that an electric field line cannot exist in conductors. That's very important. If you have a conductor, like a piece of metal, a piece of copper, a piece of steel, it's a conductor. A conductor means that electric charges can freely travel through this conductor without any hindrance. And so if there is an electric field line which goes through the conductor, that is impossible. Why? Because any small charge here, any electron here, will experience a force acting on it, and it will move. But in electrostatics, according to the definition of electrostatics, no movement of charges is possible. In electrostatics, all charges are in static equilibrium. They don't move. There is no macroscopic motion of charges in electrostatics. In static equilibrium, charges may be somewhere concentrated along the surface of the conductor, but they don't move because this is a static equilibrium. And therefore, if they don't move, there is no force acting on a charge inside the conductor. And it means that no electric field line may go through a conductor, and maybe inside the conductor. Inside the conductor, there are no electric field lines. And other important property of electric field lines is that they are always normal to the surface of a conductor. So this situation, as I put it here, as I draw this line at some angle, this is impossible if we have a conductor. And this situation is also impossible. This angle alpha should always be 90 degrees. And this is another angle beta, also should be equal to 90 degrees. Why so? That is the property of electric field lines near the conductor. Why so? Because if it's directed at any other degree other than 90 degrees, then there will be a force acting on an electron, and there will be a component of force normal to the surface and component of force along the surface. And this component along the surface will cause this electron to move, and the electron moving along the surface is a part of electric current, and there should be no currents in electrostatics. No macroscopic motion of charges in electrostatics, because all charges by definition should be in static equilibrium. So in electrostatics, all the field lines are always perpendicular to the surface, always perpendicular to the surface of a conductor. If we have a conductor, this angle alpha should always be 90 degrees. So the electric field lines near the conductor must be always perpendicular. They may be directed towards the conductor if it's charged negatively, or it may be directed outwards and out in the opposite direction if the conductor is charged positively. But the electric field lines are always perpendicular. And what happens at the corner? The corner actually, from microscopically, it may not be a corner. It should be some sort of spherical surface. And so the lines, the electric field lines, will be perpendicular to this small spherical surface. They will be perpendicular to it, and they will be directed in this way. But in each point of conductor surface, the electric field lines will be perpendicular locally to the local surface of a conductor. Because we consider electrostatics, we narrow the field of consideration. We consider only the laws of electrostatics because they are the most simple laws. And as the first step in studying electromagnetism, we must make it clear, we must clear out what happens in electrostatic in case of static equilibrium. Certainly, when we understand what happens in static equilibrium, then as a further step, we may consider the situation of non-static situation when electric currents are induced on the surface of conductor. And if electric currents are induced on the surface of conductor, this will be another situation, not the situation of static equilibrium, but the situation of dynamics, electrodynamics. And the laws of electrodynamics are more complicated, and as the first step, we don't have to consider complicated things. We have to consider simple things. The most simple thing is just the first step in studying electricity and magnetism. And the first step, as the most simple case, is the case of electrostatics, when all charges are in static equilibrium, and in this case, the electric field lines should be always perpendicular to the surface of a conductor. So the next thing we have to consider is a definition of potential, electric potential, and a definition of potential difference. Let's consider some electrostatic field, arbitrary electrostatic field. And let's put a probe charge in an arbitrary point A. The field will act on this probe charge with some force, which is equal to charge times electric field strength, vector E. Vector of force equals vector of electric field strength times the magnitude of the probe charge which is placed at this point. That is an arbitrary field, and we choose an arbitrary point. If we move this charge from this point to infinity, then the field will always act with some force on this charge, and therefore the field will perform some work on this charge. The field will perform some work. And this work, when we move the charge from this arbitrary point to infinity, this work, delta A, say delta A, is by definition called the field potential at this point A if the given charge is equal to one unit. If the charge is not equal to 1 unit, then the work will be proportional to the quantity of this charge, to the magnitude of charge. And in general case, the work performed equals the potential, the field potential at point A times the electric charge. So by definition, a field potential in point A is the work performed when we move the charge from point A to infinity divided by the quantity of this charge. By definition, that is the field potential at a given point. Let's consider a simple case when the field is created by some point charge Q. The field lines of this point charge are well known, and if we take an arbitrary point here and move the charge from this point to another point, from point 1 to point 2, then this displacement of a probe charge can be decomposed into two displacements. The first displacement will be the displacement along the radius vector, and the second displacement will be the displacement along the circular trajectory, such that the point charge capital Q is in the center of this circle. So when the point charge, the probe charge, is moved along the radius, the force acting on this charge coincides with the displacement, and some work will be certainly performed. But when the point charge is moved along the circular trajectory, which is perpendicular to the radius, the force acting on the probe charge will be perpendicular to the displacement, and no work will be performed on this displacement from along the circular trajectory. So the work performed depends only on the distance along the radius. The work performed depends only on how far we go from the central charge. And it does not depend on how far we go along the circular trajectory for which the central charge is in the center of this circle. It means that the work performed here from point 1 to point A, for example, is non-zero, while the work performed from point A to point 2 is 0. Whatever point 2 is chosen on the trajectory, on the circular trajectory. Therefore, the work performed will be the same if we go from point 1 to point A, or if we go from point 1 to point 2, or if we go from point 1 to point 3, or from point 1 to point 4, etc. All these works performed on these trajectories will be the same, and they will be defined only by the work performed on the radial motion, the displacement along the radius, but not the displacement along the circular trajectory. So the work performed in an electric field does not depend on the trajectory, in the sense that the work performed on all these trajectories is the same, and the work actually is defined only by the distance from the initial position of the probe charge from the central point charge and the final position. So the initial distance d1 and the final distance d2. Only the change in distances will define the work performed, and not the displacement in a perpendicular direction. Therefore, any trajectory from this point to this point will have the same work. Either I go along this trajectory or I go along this trajectory. Any arbitrary trajectory will give me the same work, which is equal to the work performed on this short displacement d2 minus d1. For this reason, the work performed in an electrostatic field depends only on the initial point and final point, actually only on the change in distance from the central charge, and does not depend on the trajectory. It means that we may choose any trajectory for motion of the probe charge. We may move the probe charge from this point A to infinity using the direct line to infinity, or we might go using any line. If we go to infinity, the work performed will not depend on the trajectory. It will depend only the initial and final position of the probe charge. That is why this concept of potential, field potential, electric field potential at a given point A makes sense. This quantity makes sense because it does not, the work performed does not depend on the trajectory in an electrostatic field. If we have 2 points A and B in an arbitrary electrostatic field, then in the first point we have a field potential phi A, and in the second point we have field potential phi B. And if we move a probe charge from one point to another, then the field will perform some work. And this work is proportional to the potential difference, potential in one point and field potential in another point, and the work performed between 2 points will be potential will be defined by potential difference, or it's better to say by definition the potential difference between these 2 points phi A minus phi B is defined by the work performed divided by the value of probe charge. That is the definition of potential difference between 2 points in an electrostatic field. That is the definition of potential and potential difference. There are 2 different quantities. A potential is a potential difference between given point and infinity. A potential of a given point is the potential difference between given point and infinite point. But if we take 2 points, none of which is at the infinity, then the potential difference is defined as the ratio of the work performed by the forces of electric field to the magnitude of the probe charge which has been moved from point A to point B. So I give you some formulas. If we have a field of a point positive charge plus q, then the field potential at the distance r at this point, the field potential here as a function of distance from the point charge will be given as coefficient k, which is in international system equals 9 times 10 to the power of 9. And the central charge q divided by r. So that the field potential as a function of r will be given by such graph. It's inversely proportional to r, the field potential of a point positive charge. If we take the negative charge, then the charge will be negative, and the graph will be just the same but negative multiplied by -1. So that will be the field potential in the negative for the negative charge, defined by this formula. That I give you without derivation. That's just a formula for field potential of a point charge. If we take any conductor of arbitrary form, that is a piece of metal, for example, a piece of copper, a piece of steel, well, anything, a piece of conductor, then no field strength, field lines can exist inside the conductor. We discussed it already. In conditions of electrostatic, no field lines can exist inside the conductor. It means that no forces act on a charged, on an electron, on a single electron. No electrostatic forces act if the electron is inside the conductor. No forces, because if there is a force, then the electron will start moving, and any motion will give us the situation other than electrostatic, other than static situation. In static conditions, the charges don't have any macroscopic motion, don't move macroscopically. They can move only due to thermal motion, but no microscopic currents should exist in electrostatics. So no forces act on charges inside the conductor, and therefore no field is inside the conductor. And therefore, if I take the electron or a small charge and move it inside the conductor from one point to another, then no work is required, no work will be performed by the field forces, because forces are equal to zero. The electric field forces are equal to zero inside the conductor. And so the work performed on displacement of any charge is zero. And for this purpose, if the work is zero, if this is zero, then the potential difference is zero. So potential difference between any 2 points, point A and point B, is zero. The potential at point A, the electric field potential at point A equals the electric field potential at point B. It means that all the conductor, the piece of conductor, is always at the same potential. Potential difference between any 2 points is zero. The potential, the electric field potential is the same for all the points of electric conductor. And if we take an electric conductor in a special form, like a metal plate and another metal plate, then 2 parallel metal plates forms a capacitor. 2 parallel metal plates will form a capacitor. And if we take some charge, few electrons from the lower plate, and put them on the upper plate, then the upper plate will have an excess of electrons. It will have some negative charge, minus Q, and the lower plate will have some excess of positive charge, so it will be charged positively. And if the field lines must be perpendicular to the surface of conductor, the field lines must be perpendicular here, and also they must be perpendicular here to the surface. Therefore, the field lines will be just straight lines inside the capacitor. The field lines will be straight lines inside the capacitor. The field will be uniform. We say uniform electric field inside the capacitor. So if there is some electric field strength inside the capacitor, and the distance between the plates is d, then any probe charge put inside the capacitor will experience force, will be acted upon by force F, which will be equal to the field strength and the probe charge magnitude. And the work performed by on displacement of probe charge from one plate to another plate, the work performed will be equal to F times the distance d between the plates, and that will give us E dq. And for this reason, the potential difference between 2 plates, the potential of the first plate, and let it be the first plate, and the potential on the second plate, and we consider the potential difference between the two plates. Potential difference between the two plates will be equal to, by definition, this is the work divided by charge, and that will be ED, the potential difference between the two plates. The potential difference on a capacitor is usually called a voltage, and sometimes it's denoted by capital U. So for a capacitor, we may say that the voltage on the capacitor plates is the electric field strength inside times the distance between the plates. And the voltage is measured in volts. The voltage is measured in the units volts. And for this purpose, for this reason, electric field strength is measured in volts divided by meter, as follows from this formula. Electric field strength should be measured as volts divided by distance, which is measured in meters. So that is as far as the voltage on capacitor plates is concerned. Next time we will consider more issues related to capacitors and connections of capacitors, and we will solve some interesting problems on the topic of electrostatics. And on this note, we come to the end of this lecture, so let's finish it. Goodbye till next time.